Circling back to section 8.3, we'll be talking about matrix inverses today. When you think about the inverse, we probably should talk about an identity first. An identity is just something that doesn't change something. It keeps its own identity. So like 12 times what equals 12? 12 times 1 equals 12. Negative 137 times what equals negative 137? Negative 137 times 1 equals negative 137. And we've already kind of talked about what identities are as matrices. Do you remember when we multiplied by this special type of matrix that we wound up keeping our matrix unchanged? We talked about that when we first talked about multiplying matrices, about how that diagonal of ones is going to produce a matrix that is unchanged. That's our identity matrix. The reason I bring that up is because we need an identity in order to think about an inverse. The identity of 1 means that the inverse would be 12 times something to equal 1. See how we needed the 1 in order to think of what an inverse would be. 12 times 1/12 is 1. So 12 and 1/12 are multiplicative inverses. Negative 137 times negative 1/137 is 1. And so our question is, how are we going to come up with inverse matrices? Well, we need to figure out a matrix times an inverse matrix so that when we multiply them, we get 1. Or in matrix world, this is the 1 matrix, right? The identity matrix. So we need to try to come up with a new matrix that would equal 1. The question is, how are we going to do that? Well, as usual, there's a way to figure it out with our brains and a way to do it on our calculator. And of course, we're going to do both. First, I want you to look at these inverses that I used my calculator to find. I wonder if you can figure out how, is there a pattern? So if your matrix is 4297, its inverse is 7/10, negative 2/10, negative 9/10, 4/10. I'm pausing because I'm hoping that you're trying to see what the pattern might be. How are they coming up with these inverses? Does anybody else think like the 4 and the 7 are switched around? The 1 and the 8 are switched around. But then the 2 and the 9 aren't switched around, but they are negafied. And then somehow a 10 showed up. Same thing on the B, right? The 5 and the negative 3 got negafied, and a 23 showed up. And, well, C maybe had some fraction involvement. Well, there's a big glaring hint in the box. Something about determinant. Do you remember how we found determinant? A times D minus B times C. What is the determinant of this matrix A up here? It'd be 4 times 7 minus 2 times 9. Dang, is that where that 10 came from? See all those 10s that showed up? And the determinant of B? 1 times 8 minus 5 times negative 3. That is 23. Is that where all those 23s came from? All right, maybe you've cracked the code, but here's how we find the inverse of a 2x2 matrix of the form ABCD. Well, first of all, we switch the A and the D entries. And the B and the C stay put, but they get negafied. And then don't forget we have to divide everything by the determinant. So maybe the easiest way to write that would be, we'll just multiply by the scalar 1 over the determinant. I'll call this matrix A. So that's kind of the formula for finding an inverse. Switch, negify, divide by the determinant, you got it. Let's practice one. Find the inverse of matrix A. So it might be smart for us to find the determinant first. 7 times 5 minus 1 times negative 3. Determinant is 38. So, and here's the notation they use for inverse, kind of like how we use F inverse. I'll just go ahead and put the fractions in, I think. So the 5 and the 7 switch, so we'll have a 5 over 38 and a 7 over 38. The 1 and the negative 3 stay put, but they negify. So negative 1 over 38 and positive 3 over 38. That should be my inverse. Verify by multiplication that A and A inverse are inverses. It's kind of like checking my work now. Could do this on my calculator, but I'm going to try to use my brain. 7 times 5 38ths, 35 38ths, plus 1 times 3 38ths, 35 38ths plus 3 38ths would be 38 38ths, which is 1. Oh, this is going well so far. Do you know why it's going well so far? Let's go to this next entry. So that would be first row, second column. The 7 times the this, the 1 times the this. That'd be negative 7 38ths plus 7 38ths is 0. Hopefully you're seeing what I'm seeing. Down to the bottom row. The negative 3 times this, the 5 times this. Getting a negative 15 over 38 plus a 15 over 38. That's nothing. And bottom row times second column, negative 3 times negative 1 is 3. 5 times 7 is 35. 3 plus 35. 38 over 38 is 1. And what did we find out? That's the identity. And two inverses should always cancel each other out and make 1. They should multiply to make the identity. So we did it. We verified. I just wanted to show you one other thing that might confuse you. When we do the inverse of this one, I'm getting a determinant negative 6, negative 18 minus negative 18. The determinant comes out to be 0 on this. Do you see why I might have a problem? If I start trying to divide by a determinant of 0 after doing my switch and negify, we can't divide by 0, yes? And so this is actually a matrix. We don't have this much for numbers, except for maybe the number 0. It has no inverse. This matrix has no inverse. So a determinant of 0 means a matrix has no inverse. Wild and crazy. Let's see an application of inverses. We talked about how we could set up a system of equations using a matrix equation before. 3 times x plus 1 times y equals 0. That was that top equation, right? We talked about this and how to set those up. We never talked about how to solve them, though. And so the question is, how do we get this by itself? How do we cancel out a 3, 1, 4, negative 2? Well, we need to do the opposite of 3, 1, 4, negative 2. It would be its inverse, right? Should we grab our calculator to find the inverse this time? We could do our switcheroo and our negify and divide by the determinant, but let's practice the calculator. For inverse, you'll actually just be able to go to matrix, have the A show up, and your calculator is smart enough to know that like this x to the negative 1, that you mean it to be inverse this time, that you don't mean an exponent of negative 1. So I guess that's a pro. So when we hit that, it will give us the inverse matrix. If you'd rather see those as fractions, do you remember how to get decimals into fractions? Math frac? We can do that too. It'll change a whole matrix into fractions for us, if you'd rather see that in fraction form. So my plan here to cancel out the 3, 1, 4, negative 2 is to multiply both sides by the inverse. Notice because multiplication is not commutative, I had to put it in front of both sides. I wouldn't be able to put it in front of one side and in the back of the other. So I put it in front of both sides. What we find out is that these will cancel. Well, technically, they'll make 1, 0, 0, 1, right? And what's 1, 0, 0, 1 times xy? Should just be xy, right? So usually we don't even write that part. So those kind of cancel each other out, and then we just multiply these two together and we should have our answer. Whether you do that on the calculator or whether you do that by hand, up to you. They definitely will multiply together, and our answer should be 2 by 1, which is good because I was hoping for an x and a y. This might be faster just to do by hand, right? First row, only column, 0 times the first one, 10 times the second one would be a 1. 0 times the first one, 10 times the second one would be a negative 3. I am fairly confident our solution is 1, negative 3. Go ahead and check that in our equations up above. Feeling good about it. So now we have two ways to solve systems using matrices. I just want to review quick those two methods. Our first method by hand was all that Gauss-Jordan elimination, but we know in our calculator we can just use the RREF button. Our second method is we could take the matrix equation and then get rid of this matrix by multiplying by the inverse on the other side. So the inverse of the coefficient matrix times that solution matrix, should we call it, over here, should give us our x, y, and z. You could try these both ways and you should get the same answer. Which one do you think would be faster for you to type in? And finally, we haven't talked about how we would find an inverse of a 3 by 3 matrix, only a 2 by 2 so far. We know we switch the A and the D, negify the B and the C, divide by the determinant. But for a 3 by 3, it's a little more complicated. The method that I've always seen is that you use a doubly augmented matrix. And then your goal is to clear out your two triangles on this side, which will then totally screw up this identity matrix on the other side, but in the best way possible, so that when you're all done getting all of the zeros over here, this side turns in to the inverse. It's glorious. I kind of love it. If you're interested in why that works, it's because we are just looking for a matrix times a special matrix that will make the identity matrix, right? Well, we know that when we're taking a matrix equation, that's the same as an augmented matrix put into an RREF form. Well, this is a matrix equation. It's just a bigger augmented matrix. And so if we put that into RREF form, our solution winds up just popping out right there, and that becomes our inverse. It's kind of cool, and you get to try it today.